So today is this first lecture on vector. So vector introduction. So in this topic I will be covering basics of vector addition, scalar multiplication, basis vectors, and all the basic introductory stuff regarding vector. Okay, so the first question is, what is vector? Okay, so most of us who is watching this lecture are most probably from science background, and the first thing come to our mind uh, l- when we take the name vector is an arrow, right? So many of us has studied 11th and 12th standard physics, and in that vectors are heavily used, right? So uh, just give me a minute. So in physics, vector is something like this, and it has two things. One is magnitude, which is the length of the vector, right? It's the length of vector. So length of the vector represent the magnitude, the amount, and the another thing is direction. Toward it, it points toward the direction, right? So a vector, like, it can represent a force. So for example, this vector may be a force vector. So the length of this vector is representing the magnitude of that force, and the direction of the arrow represents in which direction that force is applied. So maybe we have a box, and if I apply force in this direction, so I am saying, okay, there is a force applied in towards this direction, having this magnitude. And let us suppose I applied another force in the same direction, but the length of the vector is twice. So I say that, okay, the magnitude of that force is 2 times as compared to this one. Similarly, I can provide force in this direction as well, right? So this is vector in physics. uh, Apart from this vectors, if any one of you is from programming background, so there are vectors in programming language as well. So for example, in C++, uh, we have vectors. In C++, we have vector. So in C++, the vector is nothing but it is a list of entity or objects. So for example, it could be list of integers 1 2 3 and so on. It could be list of strings as well, like a b c e f g something, right? It could be strings of custom object. Maybe you have a object of class or something. So anything basically. Vector is in C++ vector are a list of some objects, right? Now coming to maths. So in maths, vector is a more broader and abstract concept. Okay, in maths, it is generally associated with the coordinate system. So for example, we have this coordinate system, the xy coordinate system, right? So if I have a point here, let us suppose this is point 2 comma 2. Okay, so this is the coordinate plane, xy coordinate plane, and this point is 2 comma 2. So we can represent this point as a vector also. So this point as a vector, and it can be written as 2, like this. So here in maths, this vector 2 comma 2, it can be treated as a point 2 comma 2 in the xy plane. So this vector is nothing but pointing to that point. So the tip of this or head of this vector is at 2 comma 2, and its tail is at origin. So all most of the time in maths, these vectors has tail at the origin. Okay, and also this is called column vector. Now you may be saying, why column vector? Because there is also something called a row vector, which is like this, which is written as a row. This is column, right? Vertically is column and horizontally is row. So this is row vector. So I will come to this row vector thing later when we study matrices. But right now you can treat this any vector as a column vector. Okay. So basically, any such vector x comma y is nothing but you can say it's a vector in a 2D plane whose head or whose tip is at that particular coordinate x comma y, and tail is always at origin. Okay, similarly we have 3D vectors also. So we have 3D vectors in 3 dimension x y z. So for example, we can have this 1 1 1. This is a 3D vector, so it's in the 3D plane, 3D xy plane, right? So maybe somewhere here in the 3D space. So now okay, now there are primarily two things associated with vectors when we talk vectors in mathematics. One is vector addition. One is vector addition. Sorry, it's too. Sorry. One is vector addition and another is vector multiplication. Okay. So what is vector addition? So for example, we have this coordinate and we let us suppose we have two vectors. This is vector and vector is denoted by this as this, right, in maths. And let us suppose we have another vector b like this, and we need to add vector a and b. So let us suppose we add vector a and vector b to get vector c. Okay, so how we are going to do is, the way we add vectors, there are two interpretation to it. One is this arrow interpretation. So what we do is we take the first vector as it is, this is the vector a, and we move this b vector such that its tail, this b's vector tail is at the tip of a vector, something like this. So if you see, I just moved this b vector parallelly such that its tail is now at the tip of a. So and then we join the tail of a with the tip of b and we get this vector c. So this is how vectors are added. And in terms of numbers, how it is added, for example, the vector a is, let us suppose it's a1 a2, it's 2D vector. Then how we are going to add is with b is b1 b2. It's simple, like we will simply add the x component of both the vectors, a1 plus b1, and we will add the y component of both the vectors, a2 plus b2. So you must have realized that vector addition should follow one rule, that if we are adding any two vectors, their dimension needs to be same. We cannot add a 2D vector, let's suppose a1 a2, with a 3-dimensional vector. It's not possible. Their component, their dimension needs to be same. Okay, right? So this is vector addition. So there are two interpretation. One is this normal vector, this as a column vector representation, where we just add the x component, add the y component, and this scales to any dimension. If we have 3 dimension, then we add all the elements across the dimension. So we will add all the x components, all the y components, all the z components. Okay, and there is this arrow interpretation as well, where we move this b vector such that the tail of b vector is placed on tip of a vector, and then we join the tail of a vector with tip of b vector. Okay, now what does this even a vector represent? If I say I have this a vector, right? So see, it represents something. Maybe in terms of physics we can say it represent some motion, right? So if I'm saying that, let us suppose the coordinate of a vector is 2 comma 2. All right, so it is same as if I am moving along this a vector in this direction, or I can move like this, first in this direction and then this in this direction, right? If you do same, you will end up at the same location. Okay, so I think vector addition, it's very simple concept. It is clear to you. Now the second concept is also very simple, is scalar multiplication. Scalar multiplication. So given a vector, let us suppose this is a vector a, I can multiply a vector with a scalar. So this is a vector, I can multiply it with a scalar, let's suppose 2, and what I get another vector b whose length is twice as a. So I will get another vector b whose direction is still same, but it is twice in length as compared to a. And this scalar could be anything, lambda, right? This scalar lambda could be anything. It could be integer, all right, it could be float, it could be anything, but it just need to be a number which can be multiplied. And how we do multiplication on a column vector? For example, we have this column vector a with a1 a2 as a xy components. If I multiply it with a scalar lambda, then this scalar will be simply multiplied by all the components. So it will be lambda a1 and lambda a2. Okay, now let us suppose instead of multiplying by 2, if I multiply it by -1, so -1 into vector a, so what will happen? Let us suppose this is another vector c. So because see, if you check, this number has two components. One is the magnitude, which is 1, and another is the its sign, which is negative, which represent negative direction. So the magnitude wise, c vector will be of same length as a, but its direction will be flipped. So now c vector will be somewhere here. Okay, so these two, vector addition and scalar multiplication are the two most fundamental operations in LA. LA is basically linear algebra, right? So now in scalar multiplication, what this lambda is doing, it's kind of stretching. If this lambda is greater than 1, it is stretching the vector, right? And if it is less than 1, it is stretching. If it is less than 1, then it is squashing the vector, basically compressing it. And if it is 1, then it is doing nothing, right? And the same goes for negative, it just that the direction get flipped. So let us suppose if it is -2, then basically it stretches the vector by 2 times and flipped it. Okay, so I think these two concepts are pretty basic and fundamental as well. So it's very easy to understand both these concepts, both from the interpretation of vector as an arrow, and also as a column vector, as a list of number. The next thing is basis vector. What are basis vectors? And this is very important, especially from in next lecture, when we will be explaining what is span, what is linear transformation, all those things. Then in that, basis vector plays a very important role. So if you remember that when I draw this vector 2 comma 2, I said that what we can do, instead of considering it as a 2 comma 2 vector, what we can do rather is treat as a combination of two vectors. This is the one vector and this is another vector, right? So kind of moving first along this direction and then this direction. And if you write down this vector, this is nothing because where it is pointing at this. So this is nothing but 2 0 because this point to this coordinate 2 comma 0, and this is nothing but 0 comma 2, right? And also this also goes with a definition. This also goes with a definition of vector addition, which says that if I simply add these two vectors, that is first along the x direction and then along the y direction, what I get according to vector addition is 2 2, which is same as the original vector. So this you can treat as we have decomposed a 2D vector xy into two components, one as x0 and another as 0y. Right? So this is vector decomposition. Where we split one vector into multiple vectors as a linear combination. This is nothing, and also this is nothing but a linear combination. I will explain it further in the upcoming lecture what is linear combination. But yeah, vector decomposition, we decompose a vector into multiple vector, and those multiple vector can be linearly combined to get this original vector, right? So we can do this for any vector and any dimension. This is true for 3-dimension case as well, x, y, z. In this case, either I can do this decomposition. Each vector can be decomposed like this, right? And I can do this as well, maybe one in xy and one in z. There are multiple ways of doing, but yeah, this is also valid vector decomposition. So now if I break this further, right, let's break it further. Let's break it to the most fundamental thing. This is I wrote as 2 0 plus 0 2. Can I write this as 2 1 0 and 2 0 1, right? I can do this. And what is this? This is nothing but scalar multiplication, which I just explained, and this is nothing but vector addition. And in scalar multiplication here lambda is 2. So what I am doing here is I am taking two vectors 1 0 and 0 1. I am first doing a scalar multiplication by 2, which is nothing but I am stretching both these unit vectors 2 times. So and what these unit vectors are, these are nothing but this 1 0 and this 0 1, right? So I'm stretching them 2 times. Okay, so I am simply stretching it. After stretching it, this becomes this 2 0, and this becomes this, sorry, 0 2, right? And then after doing this, I am combining both these stretched vectors. Now there are no more unit vectors. Unit vector is 1 0 0 1. After doing scalar multiplication, these become stretched unit vectors, so I will call modified vectors. And then I am doing a vector addition, which will gives you simply just place this vector here, that is tail of this vector, the tip of the second vector, and you get this. And similarly you can do another way also. You can move this bottom vector 2 0 to here, that is the tail of vector 2 0 at the tip of vector 0 2, and then you will get the same result. There are two ways of doing it. So this 2 comma 2 has been decomposed to 1 0 and 0 1, and then there is some linear combination of these two fundamental unit vectors to give you 2 comma 2. What these vectors are called? Basis vectors. And in this case 0 1 0 and 0 1 is nothing but basis vector for 2D coordinate system or 2D plane, right? So any vector, any 2D vector xy, any 2D vector xy can be decomposed into these unit vector 0 1 as a linear combination. This is right? X into 1 0 plus y into 0, and this is linear combination, by the way, but I will explain it in detail what is linear combination in upcoming lecture. And if you are coming from physics background, you know that this we also call as I hat, and this we call it J hat. And this entire interpretation is valid for 3D also and 4D also, for any number of dimension. We generally consider 2D and 3D most of the time because they're easy to interpret. In case of 3D, I hat become 1 0 0, your J hat become 0 1 0, and your K hat becomes 0 0 1. So in 3D, any vector x y z, any three-dimensional vector x y z is nothing but a linear combination of these three basis vectors I, j, k. Okay, so this is very very important statement, that any vector, any 2D vector v in xy plane is nothing but is a linear combination of basis vectors I hat and j hat, or 1 0 and 0 1, and that's why it's named it like basis. Basis means the base. Basis is a word which is originated from base. Basis is originated from base. Base is like at the bottom. What is the denominator? So the denominator, the bottom, the most fundamental thing of a 2D plane, 2D xy plane is nothing but these two vector 1 0 0 1. So I think basis vector is very clear to you now. What is basis vector? Because this concept of basis vector is very important to understand further concept like linear combination, linear transformation, span. What is a span of vector, spaces, and all those things, right? So yeah, that's all for today's lecture. I covered the basic things: vector, vector addition, scalar multiplication, and basis vector. Okay, see you next time.